We are going to look at a thermal physics question for year 13 physics. Pause the video now and try all parts of this question. So part A is a standard definition explaining what is meant by the specific latent heat of fusion. So you need to learn this definition off by heart, and it's usually a 2-mark question. So it is the energy required to change 1 kilogram of substance from solid to liquid. Now, that is where a lot of people finish. That is not the full answer. The full answer is with no change in temperature, because it's really important that you understand that when there is a state change, there is no temperature change. And we often see these graphs that look like this, where we have temperature rise and then a state change, temperature rise, state change, etc. So it's really important that you put that in. Now it's fusion, so that means solid to liquid or liquid to solid. If it was vaporization, then it would be liquid to gas or gas to liquid. Part B is a fairly standard calculation for year 13. So they're asking you to work out the rise in water temperature with a pump. Now, it's a 2-stage calculation, which is pretty common. Actually, maybe it's 3 stages because we've got power here. So when we have heat capacity and we have a rise in water temperature, we should be able to write down straight away this equation: energy, mass, heat capacity, temperature change, and we can obviously rearrange for temperature change. But importantly, we don't know the energy and we don't know the mass. We've got to do 2 extra steps. So to work out the mass, we need to say that is density times volume. We've been given the density of water. So that's 1,000 times by the volume, which is 5.5 meters cubed. So that's going to be 5,500 kilograms. And to work out the energy, well, that is power times time. We've been given the power here. We've been given the time here. So that's 2.2 kilowatts. So times 1,000 times 2 hours. But we want that in seconds. So 60 minutes times by 60 seconds. So let's just quickly type that in our calculator. 2,200 times 2 times 60 times 60 is a huge number here, which we would expect for 2 hours of heating, times 10 to the 7 joules. So now it's just a case of plugging that into the equation here. So 1.584 times 10 to the 7 over 5,500 times by the heat capacity of water, 4,200. And that will give us our temperature change. Which is 0.7. That doesn't seem quite right. That seems very small. So I'm just going to do a quick check. Have I made any mistakes? 5,500 kilograms. Power times time, 2,000 times by 2 hours. I'm just going to type that one more time in my calculator. Get the same answer, so I assume that is indeed correct. So maybe when I was writing this question, the numbers I picked maybe were a bit silly, maybe. Okay, part C. The pump can circulate the water at different speeds, and working at higher speeds, the rise in temperature is greater. Explain why. Again, assume that no heat is transferred to the surroundings. So there are a couple of ways you could approach this, but the most obvious way is to say when the pump is working, it is doing work on the heater. So when we do work on something, we can increase its temperature. So work will increase the temperature of the water even further. Okay. I guess in simple terms, what you could think of is, when the pump is working, it's actually making the water move faster. It's making the water, collide with itself. And so we're actually increasing the internal energy of the water because we are giving the water molecules more kinetic energy on average. And obviously, temperature and kinetic energy are related to each other. You could also think of it in terms of wasted energy. The more the pump is working, potentially the more waste energy there is, the more waste heat there is. And where is that waste heat going to go? Actually, it's just going to go into heating the water further as well. And actually, in this case, although we might say there's waste heat, actually it is useful because the whole point of this is to heat the water. But this is probably the most technical way to word it because we're talking about work, and obviously this relates to the first law of thermodynamics, which is usually expressed like this. So energy flow is internal energy plus work